Hello Lancers, today we're going to be practicing solving kinematics equations, and it's real important that you follow along and pay attention because I want you to be able to do this well on your test and on your quizzes. So this is an important skill that we get, and it's not all that hard, you just follow the steps, okay? So we have three main kinematics equations. All three of these are for uniform acceleration, meaning the object's accelerating at the same rate the entire time, because they all have an A in them. We know that they're all talking about acceleration. The top one relates position and time, the next one velocity and position, and the bottom one velocity and time. So they relate different things, but they're all for uniform acceleration. If you don't have any acceleration, if A were to equal 0, well, that term would go away. You'd have delta x equals vt. Divide by time, and you would get that the velocity is equal to the displacement over time, which is the equation we used a little bit probably early on because it's your constant velocity. So when acceleration equals 0, we can use that one. With uniform acceleration, we typically use these three. Today's examples are going to involve things that are in a gravitational field, so they're falling down or accelerating. So in all those cases, it will be uniform acceleration. In this case, uniform acceleration due to gravity. Let's go ahead and get started with our first example. All right, so our first example. A cheerleader is tossed upward from a basket toss. If she goes 3.4 meters straight up, what was her initial velocity? So in our question, we can draw a little sketch to sort of visualize what's happening. In this case, we have a cheerleader. So here's my cheerleader. She's being thrown upward from a basket toss. Notice your diagrams do not need to be super complex. Just a little stick figure with an arrow. I know she's going to go up and probably come back down, hopefully being caught by her friends. We need to make a list, and this is the first step in solving a kinematics problem, is to make a list of your known variables and as well as what you're solving for. So making the list is the very first step. The list, well, what do we know? What can we put in here? If she goes 3.4 meters straight up, what is that? The unit might be a big clue, meters. Meters is the unit for displacement, so delta y equals 3.4 meters. That is a displacement vertically, how far she goes. We can sometimes, for displacement, use delta x if it's a horizontal displacement. You will also see with your displacement that that can sometimes be a d. Now, I try not to use d for displacement. I used to use it quite a bit. You may see it occasionally in my materials. But most people today are using delta y or delta x. Delta y for vertical displacement and delta x for horizontal. Okay? There are no other numbers given. Does that mean that we don't know anything else for our list? Actually, there's two more numbers sort of hidden in there. And we need to pay attention. It says how she goes 3.4 meters straight up. And so we're probably talking about this position at the top of her throw. Now, what do you know about something at the highest point and when it's under the effects of gravity? Well, we know that while it's going up, it has a positive velocity. While it's coming down, the velocity is negative. What's in between positive and negative? 0. The object actually has to stop for a moment at the highest point. So we would know at the highest point, which we would call the final in our situation, the initial will be down here, but the final point, the velocity would equal 0 meters per second. We know something else, or at least we assume something else. We assume that the cheerleader is on planet Earth. If you change planets, you change your gravitational field, gravitational acceleration, but here on Earth, we can assume it's going to be 9.8 meters per second squared. And so I can go ahead and put in here g equals the acceleration, because on Earth, the acceleration is going to equal g, which equals 9.8 meters per second squared. And then finally, what are we looking for? What was her initial velocity? VI equals question mark. And so I have in my list the acceleration, because we can assume it's the Earth. The final velocity is 0 at the highest point. The displacement was given, and I want to find the initial velocity. This is the second spot where we need to go ahead and apply a little bit of we need to go ahead and pick a formula using our formula sheet. Now, I was going to say use a trick or something, but it's really nothing tricky. You simply take the items in your list. We have a displacement, a final velocity, an acceleration, and initial velocity. And what formula has those four things? Go ahead, take a look at your formula sheet. Figure it out. Which one has those four things? Did you get Vs squared equals Vi squared plus 2A delta Y? So notice I wrote down that formula that seemed to have all of my stuff in it. And when I wrote down the formula, I didn't try to substitute numbers in for the same step. Those are two separate steps. If you try to substitute your numbers in while you write the formula down, you will typically make a mistake. People forget to include the square. They'll do something wrong. It's okay. Write down the formula without substituting your stuff in first, and that way you can get the correct answer. So our final velocity here, 0 meters per second, quantity squared. The initial velocity, I'm just going to write as VI squared. We don't know what it is. We're solving for it. Plus 2 times the acceleration. And I wrote that as 9.8 meters per second squared, but gravity is pulling us downward, so that actually needs to be a negative 9.8. Negative 9.8 meters per second squared, where the negative indicates the direction. And the displacement is positive, even though the acceleration is downward is negative. So that is 3.4 meters. It is important to note that while the person is going up, they have a positive velocity, their displacement is positive, but gravity is still pulling them down, so that's in the negative direction. Upward being the positive direction, down being the negative direction. We can do a little bit of rearranging here. 0 squared is 0. I'll move my VI to the left side of the equation. So I get negative VI squared. 2 times 9.8 times 3.4. You can do that in your head. I'm going to use a calculator. You can use a calculator too. And I get 66.64. Creepy number. All right, the unit there would be a meter per second squared times a meter, which will leave me with meters squared per second squared. And that's good because when we take the square root of both sides, we should get meters per second, which is the unit for velocity. I am going to multiply through by a negative 1, which will get rid of that negative. And then we just square root both sides, and I can have my initial velocity. So square root of 66.64, I'll go ahead and get that. And we get 8.16, 333, and it continues. But how many sig figs was I given in my question? 2. 2 sig figs in the question, so I should only report my answer to 2 sig figs. So you'd want that to be 8.2 meters per second. All right. Let's go ahead and try another one. A rock is dropped into an abandoned well. It takes 2.4 seconds to hit the water. How far down is the water? I remember when I was a little kid, my grandpa took me on a walk. We were walking through this trail in the woods. We came across an abandoned well, and he did this. It so impressed me because I had no clue how I figured out how deep the well was. But this is sort of a neat trick if you want to ever figure out how far something down is. You just have to drop something down, listen for when it hits, and do a little bit of math. Again, I'm going to start out with a diagram just sort of to help you understand the situation. There's my well, there's some water down there, and up here a rock is dropped down. There is a time, and I won't put that in my list, of 2.4 seconds. So time equals 2.4 seconds, and that's when the rock will splash into the water. And we need to figure out how far down is the water. So we're actually trying to figure out the delta y. How far down is it? Again, that's not a complete list. There's other information hidden in the question. The first thing we look for is the word dropped. When you drop something, you're implying that the initial velocity is 0. And so I'm going to write VI equals 0 meters per second because the drop indicates 0 meters per second. What else is hidden there? What planet are we on? We're on planet Earth, of course. And so what would the acceleration equal? The acceleration is going to equal the gravitational field of Earth, negative 9.8 meters per second squared. That's still in the screen. That should still be at the bottom of your screen there. Okay. What else do we know? Or what formula should we use? We got to pick a formula. Look through your formula sheet, find one that has a time of displacement. It'll probably be delta x, VI, and A. You want a formula with VI, A, delta x, and T. It's okay, the horizontal formulas work vertically just as well. So you can replace delta x and delta y. They work interchangeably, the formulas. So we have delta y equals VIT plus 1/2 AT squared. Our delta y is the vertical displacement. It's probably delta x on your formula sheet equals VIT plus 1/2 AT squared. We need to solve this for delta y. So now that I've written down my formula, did I substitute numbers in right away? No. I'm going to wait for that. Delta y equals the initial velocity. That's 0 meters per second. It was dropped. The time is 2.4 seconds, plus 1/2 the acceleration is negative 9.8 meters per second squared, times 2.4 seconds, quantity squared. What's 0 times 2.4? Well, that's still 0. That's going to be in just meters, I guess, because you have, your unit here works out to be meters times seconds over seconds. So the seconds cancel out and you're left with just meters, but 0 meters plus anything is still 0. 1/2 of 9.8 times 2.4 squared, that is negative on the 9.8. I'm going to grab a calculator. 1/2 times negative 9.8 times 2.4 squared is negative 28.224, and that will be in unit meters. So what happens when you add 0 to 28.2224? You get 0.2224. Again, our sig figs were just 2. And so I'm just going to write this as negative 28 meters. Negative 28 meters. Notice I included the unit with my answer. Your answer has to have a unit with it. Okay. We're going to do one more. Okay. This one maybe isn't as kind. You drop a water balloon 1.2 meters from the roof onto your sister's head. This should be an apostrophe. How fast will the balloon be going when it reaches her head, and how long will it take to reach her head from your hand? We'll have a double question here, so we'll have to do 2 formulas. And I'm a little limited on space, so we'll have to maybe squeeze things in. First, I'm going to sketch a diagram. There's you on the roof dropping a water balloon on your sister who is down below. So you drop a water balloon on your sister down below. in my list? We have 1.2 meters. What is the 1.2 meters? That is your displacement. What's the word drop indicate? Drop is indicating that your initial velocity equals 0 meters per second. We can assume we're on what planet? And we have, let's see, we're looking for how fast, the final velocity, and we're looking for how long, the time. I'm going to go ahead and solve for the final velocity first. So what formula has a displacement, initial velocity, acceleration, and VF? See if you can find it. Wrong formula, huh? I'm going to use this formula. So the final velocity squared equals the initial velocity, that's 0 meters per second, quantity squared, plus twice the acceleration, negative 9.8 meters per second squared, times delta y, 1.2 meters. Go ahead and figure out what 2 times 9.8 times 1.2 is. .52. Now, you're probably getting negative 23.52 because it's negative 9.8. And can you take the square root of a negative? No. Well, that's a bummer. I'm not sure what to do except for, guess what's happening here? You made a mistake. If the balloon goes down 1.2 meters downward toward the sister, then that displacement should be negative, shouldn't it? That should be negative, and that's going to make this number positive. And so it's okay. I forgot the negative there. The negative should go there. And so now we can take the square root of 23.52. And I get 4.8 meters per second. That's just over 10 miles per hour for those of you wondering how sister is doing. The last part here will be part B. I'm going to do it in red just so it's more visible. How long will it take to reach your head from your hand? Okay, well, I'm going to use a formula VF equals VI plus AT. I could use the other one as well. This formula is just going to be a little bit easier than the delta x equals VIT plus 1/2 AT squared. Since t is in there twice, you get to solve a quadratic. Doesn't seem nice. I'm going to use the easier one. I know my final velocity. I have it here now. That is 4.8 meters per second equals my initial velocity of 0 plus the acceleration of negative 9.8 meters per second squared times t. There's a second mistake I made in this one. When you take a square root, you get a positive and negative answer. And so this velocity at the bottom could be positive or negative. What direction do you think the velocity will be going when it hits your sister? Technically it should be negative, which is why the math here was looking a little funny for a second. So that should be negative as well. And we get 4.8 divided by 9.8. And I get 0.49 seconds. It would take about half a second, or t equals 0.49 seconds. Here's what I want you to do. I want want you to go back through these problems. I want to put them back on the screen without the solutions underneath them, and I want you to work them out. I want you to work it out without looking at the solution. I want you to make the list, and I want you to pick the formula, and I want you to solve it, see if you can get the right answer. Because to learn it, you really need to do it yourself. So go back through, do these problems yourself, and you will actually learn the material, and it will make you much better at being able to solve these. That's all today, Lancers. I'm Colin.